Hi, I'm Jacob. I'm one of the authors of WSInfer, which provides blazingly fast inference on whole slide images. Today I'm going to take you on a journey from beginning to end. We're going to start by installing WSInfer. We'll run it on some sample data and we'll look at the outputs in QuPath. And at a very high level, we'll be going from a whole slide image like this, actually the same one. We'll be applying a breast tumor classification model, and we will get this output on the right. And we'll be looking at that in QuPath. Great. So the first thing to do is install PyTorch. So we would like users to install PyTorch first because the installation can differ slightly based on the operating system, whether it's Windows or Mac or Linux. If you have a GPU installed, if you are using pip or conda. So PyTorch does a really fantastic job with its installation instructions. So we're going to take a look here. So we're going to install the latest stable PyTorch version. So right now I'm on Windows 11, but we'll be doing all the command line stuff in Windows Subsystem for Linux. So we're going to click Linux because that's where we're installing it. Package, we're going to be using pip to install it, Python, yes. The compute platform, so this is basically if you have an NVIDIA GPU, you will want to choose one of the CUDA options, really either one. I guess the only dependency is that your driver version is new enough, and we actually have a link to the compatibility table with those minimum versions. In my case, I'm going to choose CUDA 12.1. If you do not have a GPU, you can press CPU, but we are going to be using a GPU. CPU inference is very slow, so if you have a GPU, absolutely use it. If you don't have a GPU, you can still run everything. It will just take more time. So we're going to be essentially using this command. So we're going to start very fresh. Here's our Linux shell. In our directory, we only have slides. So we have one whole slide image. And that's from TCGA. That's from one of the breast cancer diagnostic slides. So I'm going to create a new Python virtual environment. And this will keep our WSInfer installation separate from any other environment. Great. So now let's, excuse me, we activate it. And let's just double check that we're using the right Python. Perfect. Oopsie. So now let's copy this this installation command. I'm just going to change it slightly to this python-m pip. And I like to do that because if you just use a pip install, pip on its own, then there's a chance, maybe pip is symlinked or something, and it might point to a different Python environment. So I ran this a little bit earlier, so all of these packages will be coming from the cache. In a new installation, it will be downloaded from the web. So let's see. I would like to let you all know that CUDA is installed automatically when you install PyTorch. CUDA as well as CUDNN. And this is a massive help because we as users don't have to try to find the precise version that needs to be installed, log into an account to get CUDNN. So this is really fantastic. So thank you so much PyTorch and NVIDIA developers and everyone else who made that possible. So let's go back to the WSInfer documentation now that we have installed PyTorch. We will test that PyTorch can see our GPU. So we're going to run this command here. And we should get true. Yes, we do. If you do not get true, if you get false or if an error is raised, one thing I would do, and also if you expect a GPU to be found, I would run NVIDIA SMI and double check that your GPU is listed here. So this is GPU 0. So another thing you could do is set the CUDA visible devices environment variable. So if you set it to 0 or the index of the GPU you want to use, you get true. I have one GPU, so if I set it, so I have one GPU and the index of that GPU is 0. If I set CUDA visible devices to some index that I don't have, like 1 for example, which would indicate a second GPU, it says false. So that shows you that this environment variable is very important. So if you have a GPU and it's not detected, try to set that variable. Another thing to do is check the version of CUDA that is installed with PyTorch. And here it's 12.1. If you get none or an error, then you most likely installed a CPU only version of PyTorch. So I would go back to the installation instructions and get a GPU version. Okay, great. So now that we have PyTorch installed, let's install WSInfer. So it can be installed with pip or conda. So we have the package on Conda Forge. If you don't know what conda is, that's totally fine. We're going to be using pip in this case, and this is the command here. So it's a simple pip install WSInfer. We'll wait for that. That will pull in all of the dependencies as well. And to be honest, it will also pull in PyTorch if PyTorch isn't installed. But we would like users to install PyTorch first so that they're installing the appropriate PyTorch for their system. Right, like a pip install PyTorch will not necessarily install CUDA, for example. So that's the main reason. Great. Let's see now. Let's just double check our installation. We will use the help message. And perfect, it works. So WSInfer, this command line tool is the main interface to WSInfer, at least on the command line. We also have a QuPath extension. I'm not going to be going over it in this video, but the documentation is on the QuPath documentation page. And right, the extension is called WSInfer also. So this command line tool can run patch level classification inference on whole slide images. There are a few different options and subcommands, but the one that we're going to be focusing on is run, and this is the thing that actually runs that model inference. So if I do WSInfer run -- help, here are the options. So this will run inference on a directory of whole slide images. So there are a few processing steps before the deep learning inference. So first, a tissue mask will be created for each whole slide image, and then patch coordinates will be computed. So the size of the patches is determined by the model that you're using. Models can be trained on different sizes, different patch sizes. But it's important to be consistent. So if you train on one patch size, you should be testing on the same patch size. Great, and then the results will be saved to CSV, also to GeoJSON in the results directory. And you can set the results directory. We're going to go over that right now. There are 3 mandatory options. Those are the top 3. So instead of options, let's say that there are arguments, mandatory arguments. So first is -i WSI_dir. So that's the input directory that contains the slides. Second is the results directory. -o for output shorthand, and that is a new directory to store the outputs. -m is model, and that is the model that we would like to apply. And here are the options for different models. We also have another command line tool to query models that are in the zoo. So WSInfer -zoo is the command line that interfaces with the zoo, all of the models that are hosted on Hugging Face essentially, that are part of WSInfer. So anyway, WSInfer-zoo ls to list those models, and here they are. So we have several different models. I'm not going to go over them right now. You can look at that. What we're going to do though is use this second model. It will be a breast tumor classification model. Okay, let me clear the screen. I did Control L to do that. And now we will use WSInfer-run. So for the input, slides, let's say results for the output. That's a new directory, doesn't exist yet. And then for the model, we are using that breast tumor model. I press enter, and it goes along. So a lot just happened. A lot of text popped up. The first text up here is information about the run, whether a GPU is being used, how many GPUs, the command line inputs, the versions of the software that's being used. This chunk of text, this is logs from the segmentation and patching steps. So you can read into this for the patch sizes. So for example, this model wants patches 350 pixels at 0.25 microns per pixel. And when we look down here, we have 30,619 patches. So now this below is running the model. So the model was pulled from Hugging Face into a cache directory, and that's being used here. And so this progress bar is, one iteration of the progress bar is one batch of patches. So that's why we have 957 here instead of 30,619. So if you multiply 957 by the batch size, which is up here, 32, then you'll get something close to 30,619. Okay, great. And then it also saved some metadata about the run, and in the very end, it also converted the so it makes a CSV of model outputs where each row is one patch, and it has the location of the patch as well as the model outputs for that patch. In the last step, it also converts the model output to GeoJSON, and GeoJSON is a JSON format that is great for representing spatial data. Spatial data, can include polygons on whole slide images, for example. So each of the patches is a polygon, and we associate, the model outputs with each patch, and so that GeoJSON can be loaded into QuPath. Oh. Oopsie, sorry, I did the tree of the current directory, which also showed the VN. So let's look at the results directory. So we have a masks directory. This is a tissue mask, essentially. It shows from the tissue detection step what's detected as tissue and what's detected as holes in the tissue. So the cyan, if you look into it, the cyan will be tissue. Actually, let's take a look at it. So since I'm in Windows, Windows subsystem for Linux, I'm using explorer.exe. Let's go to results, masks, and we'll open this up. Perfect. So this is a thumbnail of our whole slide image. The blue or cyan shows tissue detected regions, and the yellow are holes. So we can see that we're getting all the tissue. That's good. We're not removing all the holes, but that's okay for our purposes here, at least. I think so that step can be tuned. Great. So we also have the results. Let me show you the CSV of the results. So I'm showing it to you in Excel. Can I make this bigger? Yes. Great. So each row is one patch, and so this is the upper left of the patch, and this is the width and height. So these values are in pixel units, base pixel units of the whole slide image. And then these are the model outputs for that patch. So in this case, the model has two classes. So one of the classes is tumor, so breast tumor, and the other class is other, or not breast tumor, essentially. And if we, perfect. So this second column has the tumor values. So here you can see that they're all very close to 1. Here they're all very close to 0. If you sum these, they sum to 1. Great, so that indicates that, these patches are most likely contain tumor. I'm going to close that now, and I would like to show the GeoJSON outputs in QuPath. The reason that I'm showing this is because the QuPath that I have is in Windows, and I'm running all this in Windows Subsystem for Linux. So I would like to move everything from the WSL environment into Windows, into the Windows file system, because I've noticed that sometimes I can get some wonky behavior if I don't do that. So I'm going to copy this JSON file into here. So we have our SVS and we have our JSON file. So now I'm opening QuPath. This is QuPath version 0.4.4. And so I am opening the SVS file now. It's an HNE. Notice, this image is familiar to us. And now to load the GeoJSON, I simply drag and drop it into the QuPath window. So that's really fantastic. Thanks, QuPath folks. Very, very cool. Great, so now we can see tiles. And if you zoom in, you can see the boundaries of all the tiles. So we'll zoom out. We're going to click this button to fill the polygons. They don't fill yet, but they will once we click this. Measure and then show measurement maps. Then let's press prob tumor. And this is a heat map of the tumor model outputs. And so the yellow are regions of high tumor probability. And if we modify the opacity, we can see that the yellow regions overlap quite well with tumor epithelium. So for example, if we go here, maybe we can go to a border region, for example, here. So we have stroma here, we have epithelium here and here, and indeed, we're getting that separation. And you can threshold these, we're not going to go over that now, but you can threshold these, for example, let's say, at 0.5 to get a binary mask of tumor, as opposed to this continuous heat map. Great, so I'm going to close this now. And I don't want to forget about some of the other model outputs. Some of the other outputs here. So this patches directory, that has an HDF5 file for each whole slide image, and that has the patch coordinates, basically. So that's inspired from this directory output in general, the layout of the directory is inspired by how CLAM does things. So thank you very much. This last file is metadata about the run. So it's a JSON file with information about the run, so that basically you can remind yourself what happened here. So the version of WSInfer, in this case it's 0.5.0, and the Python version, the PyTorch version, etc. Oh, and also the entire command line interface. The command line call. So that is all. That is all I wanted to show you. Please do take a look at our documentation here. It's on Read the Docs, wsinfer.readthedocs.io. We have a table here towards the bottom of different models that are included in our zoo. We're working on incorporating more, and we would love if the community also contributed. I think that would be really fantastic, and pathologists everywhere would rejoice. We have our user guide here. Please go through that. If you have any questions whatsoever, if anything is confusing, if you find a bug, if you would like to request a feature, please go to our GitHub repository. And please create a new issue. So you would go to Issues, New Issue, and then you can enter a title and whatever you would like in the description here, whether it be, you know, like I said, bug report, feature request, question. We're always looking to improve WSInfer, so please let us know. So that's all. Thank you very much, and have fun.